So, hi everyone. I'm assuming that you have read the problem and we will directly jump to the solution. First of all, you should know some of the basic Zoro properties. You should know that if we Zor any two same numbers, let's say I'm Zoring 1 and 1, I'm getting 0. Zor of 0 and 0 is 0. Zor of 1 and 0 is 1. So these are bits. 0 Zor 1 is 1. So whenever you see same bit, when the inputs are same, I'll get 0. When the inputs are complementary or they are totally opposite, then I'll get 1. Alright. So if I say you that I have number 5 and number 5 again, so if I take Zor of these two numbers, what will be the answer? The binary representation of this number and binary representation of this number will be entirely same, and Zoring of same bit will give me 0, right? And if we have two different number, let's say 506, I will not get 0. I will get some different binary representation that will give me some different number, right? For same numbers, you will get their Zor 0. For different number, you will get a non-zero number because all the bits do not cancel each other in case of different number. Alright. Now in our problem, it is given that every number is repeating twice except two numbers. Each number has its duplicate except two numbers. So it is something like this. In array we have a number A and it is repeating 2 times, then BB, then CC, then DD, then DD. But you will have two unique numbers, let's say E and F. So every number has its duplicate except these two numbers, E and F. They are unique. So what if I take Zor of all these numbers? If I take Zor of all these numbers, A, Zor B, Zor B, Zor C, Zor D, Zor E, Zor F, we know that A will cancel A because they have entirely same bits. B will cancel B, they will yield to 0. C 0 Z, C Zor 0, C Zor C will yield 0. D Zor D will yield 0. So Zor of up to this number from AA to DD, I'll get answer as 0, right? And Zor of E and F will be something non-zero. They will not cancel each other, right? So their Zor will be equal to E Zor F. So when I Zor all the numbers, I'll get a value. Let's say that value is V, and that will be equal to Zor of these two numbers only. So by Zoring all the numbers, I have removed all these duplicate numbers. I have removed all these numbers from my array. Now I am left with only E and F. But I am not getting E and F separately. I am getting their Zored value. I am getting a Zor value of E and F. But in the problem, we have to separately send the value of E and F. Cool. Now, how to extract the numbers from their Zored value? We know that we have a value V, that is Zor of E and F. But how to extract E from their Zor value. We don't have E and F, but we have V. From that V, I have to extract E and I have to extract F also. How to extract the numbers from their Zor value? We have to think of a mechanism through which we can do it. How can we do it? Basically, we have the Zor value of these two numbers, and these two values are also present in the array, right? If we think of any mechanism, if we think of something that can differentiate the numbers, that can differentiate these two numbers, then I can get close to the answer. At least I have something through which I can differentiate these two numbers. I do not have the exact values of these numbers, but from their Zord values, from their Zord value, can I get any hint, or can I get any idea, or can I get anything from which I can differentiate these two numbers? How will you differentiate two numbers? So the hint is, think at the level of bits. Think at the level of bits. Okay. Let's do some analysis. Let's say I say you that I have a bit B1, I have a bit B2. I don't know what is the value of B1, I don't know what is the value of B2. Alright. But I know the value of B1 Zor B2. Let's say that is 0. I'm saying you that B1 Zor B2 is 0. But I don't know what is the value of B1, I don't know what is the value of B2, but I know the value of B1 Zor B2. So what are the possible values of B1 and B2? How can I get 0? What type of numbers will yield me 0? If I am getting the Zor value, this is a single bit, alright, B1 is a single bit and B2 is a single bit, okay. If on Zoring 2 bits I am getting 0, then definitely B1 and B2 are equal, because we know that we only get 0 when the bits are same. So from this I can say that B1 is equal to B2. Now B1 and B2, this can be 1, they can be 1, or both can be 0, right? It is possible. There are two cases, B1 B2 equal to 1 or B1 equal to B2 equal to 0, because 1 Zor 1 is 0, 0 Zor 0 is 0. So when the result is 0, I can say that either both are 1 or both are 0. Okay. Now, what if I say you, I don't know B1 and B2, but B1 Zor B2 is equal to 1. B1 Zor B2 is equal to 1. Can you guess the values of B1 and B2? Can you guess the values of B1 and B2? Now, by seeing 1, I can say that I only get 1 when bits are different, right? When bits are different, so this means by observing this value 1, I can definitely say that B1 is not equal to B2, right? Because when bits are different and when I Zor them, I'll get result as 1. So from this I can definitely say that B1 is not equal to B2. So here two cases are possible, B1 equal to 0 and B2 equal to 1, both are different, or B1 equal to 1 and B2 equal to 0, right? only these two cases are possible when the result is when the bit is 1. Now how this analysis help us in differentiating the two numbers from their Zord value. So we have two numbers E and F. We have two numbers E and F. They are not single bit. They can be of many bit, right? 32 bits for 4 byte integer. We have 32 bits. So this E is a 32 bit number. F is also a 32 bit number, and there's Zor value we have. And let's say E Zor F is equal to something like this. Let's say here we have some bits, then we have some 1, then we have some zeros, then we have some then we have a 1, and then let's say I have 0 0. After that, let's say I have 0 only. There is one possible value of E Zor F, right? So from right to left, if we see, when counted some zeros, then a 1. Now its last bit, or I can say rightmost bit, its rightmost bit is 0. And how will you get this rightmost bit 0? When the rightmost bit of E and the rightmost bit of F are same, right? If the rightmost bit of E or F is 0, then it means rightmost bit of E and rightmost bit of F is 0. So from this I can definitely say that E is a number, its binary representation end with 0. End with 1. If let's say if it's end with 1, then the binary representation of F also end with 1. And if binary representation of E ends with 0, then binary representation of F will also end with 0. So these two cases are possible. Either both E and F end with 1, or both E and F end with 0. Right? Either both E and F end with 1, or either both, because in that case, if I take Zor of these two numbers, I'll get 0 here at the rightmost position. If I take 0 in this case, where last bit are 0 for both of them, I'll get their Zor equal to 0. Similarly, their last second bit same, their last third bit same, their last fourth bits are same, their last fifth bit. So this is 1, 2, 3, 4, 5. So last fifth bit is 1 in our Zord value, which means the last fifth bit in my E and in my F are different. In one of the value it will be 1, and in one of the number it will be 0. So let's say last fifth bit of E can be 0, and last fifth bit of F, if last fifth bit of E is 0, then last fifth bit of F will definitely be 1. Or it can be opposite, last fifth bit of E is 1 and last fifth bit F is 0, right? So, but one thing is sure, their last fifth bit of E and F, both E and F are different. So I got 1 point of difference. 1 point of difference. That if I now, it may be possible that for some two numbers from any Zor value, last fifth bit is not set, but last second bit is set. In that case, I can say that for both E and F, last second bit is different. So, and what I will do I will find the rightmost. I will find the rightmost set bit of Zord value, and let's say the rightmost set bit of Zord value is at kth index. Okay, rightmost set bit of Zord value is at kth index. It means if this is true, if rightmost set bit of Zord value is at kth index, this means kth bit of E and F are different. One have kth bit as 1 and other will have kth bit as 0. Right. Now what I will do, in my array I have E, F, AA, BB, CC and DD, right? So I'll divide the entire array on the basis of kth bit. If a number has kth bit as set, I will put that number in group 1. Let's say kth bit of A is set, so I'll put it in the, let's say we have a group 1 and group 2. If kth bit of A is set, I will place in the group 1. So both of the A will go to group 1. If kth bit of B is set, then B will also go to group 1. Then both B will go to group 1. If kth bit of C is not set, that is 0, then I will put C in the group 2. If kth bit of D is also not set, then I will put D in the group 2. Then both D will go to group 2. And if E have the kth bit as set, I will place it in the group 1. And since kth bit of E is set, F will definitely have the kth bit that is not set, that is 0. So it will go to group 2. It will end up in group 2. So if I divide the entire array on the basis of kth bit, all the number whose kth bit is set, put them in group 1. All the numbers whose kth bit is not set, it's 0, put them in group 2. If I divide the entire array in two groups on the basis of this property, then E and F will end up in two different groups. E and F will end up in two different groups. And any two numbers who are same, who are duplicate, who are exactly same, they will also end up in the same group. They will end up in same group. B and B will end up in same group. C and C will end up in same group. D and D will end up in same group. But E and F, they will end up in different group because their kth bit is different. For one, kth bit is 1 and for other kth bit is 0. And if I take Zor of group 1, what it will give me? A single value. That may be E or that may be F. If it in group 1 E is present, then their Zor value will be E. And if I do Zor of group 2, I'll get F. If F is present in that group. So I have to just separate the entire array in two groups and take the Zor of those two groups individually. You will get both the numbers separated. Let's take an example. Let's say in my array I have these numbers 2, 2, 3, 3, 4, 4, 5, 7, and these are their binary representation. Now if I take XOR of all these numbers in my array, that will be these 1 0 will get cancelled by 1 0, 1 1 will cancel, 1 0 0 will cancel 1 0 0. So XOR of these numbers will be equivalent to XOR of 5 and 7, which are the unique numbers. And if you take XOR of 1 0 1 and 1 1 1, you will get 0 1 0. Now if you see, its last second bit is set. So you can this index is 0, this index is 2, this index is 1, this index is 1. Okay, this index is 0, this index is 1. So at index 1 from right side, the bit is set, or I can say the second bit. This is first bit, this is second bit. So last second bit is set for 5. So let's separate all these numbers in group 1 and group 2. Let's say group 1 is the group whose last second bit is equal to 1. Here last second bit is equal to 0. So let's see in which group you will put 2. In which group you will put 2? Its last second bit is 1, so place 2 here. Again second 2 will also come here. Last second bit of 3 is 1, so this will end up in here, and both 3 will end up here. Last second bit of 4 is 0, so it will end up in group 2. Both 4 will end up here. Again last second bit of 5 is equal to 0, so it will end up here 5. And last second bit of 7 is set 1, so it will end up in group 1. So you can see that I have separated 7 and 5 into 2 different groups. Group 7 is in entirely different group, and group 7 value 7 is an entirely different group, and value 5 is an entirely different group. So I have segregated 7 and 5 on the basis of this kth bit, rightmost set bit. So all those values whose rightmost set bit is 1, place them in group 1. All the values whose rightmost set bit is 0, place them in group 2. And how we got the rightmost set bit from the XOR value, and if the rightmost set bit of XOR value is set, then that means rightmost set the bit at that position in both the unique number are different. That's why we are able to segregate them into 2 different groups. Now just take XOR of this group 1 and just take XOR of this group 2 individually. So if I take XOR of group 1, 2 will cancel 2, 3 will cancel 3, and I'll end up with 7 only. So I'll get the value 7. And here cancels 4 with 4 and 5 will left. So XOR of group 2 will give me 5 only. And then return 7 and 5. That will be our answer. Now one more thing that is left here is how to find the rightmost set bit. I'll do XOR of all the numbers. I'll get the XOR of 2 unique numbers, but how can I find the rightmost set bit? Let's say my number n is something like this: 1 1 1 0 1 0 0 0. How will n minus 1 look like? What if I subtract 1 from these numbers? 1 from this number. Let's do it. So let's do the subtraction. 1 1 1 0 1 0 0. Let's see what happens if I subtract 1 from it. Now I can't subtract 1 from this 0. So I have to take carry from this 0, but it also does it is also not having any 1, so it will take carry from this 0 and it will take carry from this 1. So eventually this 1 get reduced to 0 and we will get a carry 1 0 at here. So this 0 will become 1 0. And what is 1 0? 1 0 is actually 2, right? So if I subtract 1 from it, it will become 1 only, because 1 0 is what? 1 0 is 1 0 in binary is equivalent to 2, right? And subtract 1 from this 2, I'll get 1, and binary representation of 1 is 1 only. So if I when this will give me a carry of 1, this will become 1 0, and when I subtract 1 from this, it will become 1 again, right? Because 1 0 is 2 and 2 minus 1 is 1, so this will get 1 0, and again subtract 1 from it, we'll get 1 0 here. Okay, so subtract 0 from here, it will become 1 0. Now give this carry to this 0, so 2 minus 1 is 1, this will become 1 0. Now 2 minus 1 is again 1, and this will become 1 0, and we know that this 1 0 is nothing but 2, right? So 2 minus 1 is 1, so 2, this 2 and this 1, so I'll get 1, right? So you can write 1 here, and here I'll just have 1, then 1, then 0, then 0, and all bits are exactly same. So I got subtraction of I got n minus 1 as something like this: 1 1 1 0 0 1 1 1. Now what is the difference between n and n minus 1? If you observe, bit till this point are same. It have 1 1 1 1 0, it also have 1 1 1 0, but after that bits are exactly opposite. 1 is complemented to 0, 0 is complemented to 1, 0 is complemented to 1, and 0 is complemented to 1, right? And this 1 is rightmost set bit. This 1 is rightmost set bit. So before this rightmost set bit, all the bits are exactly same in n and n minus 1, but at and after this rightmost set bit, all the bits are exactly opposite. So in general, if my number n is of something like this, a is some combination of bits, then I'll have rightmost set bit 1, then I have some zeros. Okay, so if I do n minus 1, these all these bits which I'm denoting by a, which are before rightmost set bit, they will remain same. This 1 will be complemented, it will become 0, and all the bits after this rightmost set bit, they will also get complemented, they will become 1 1 1, right? And if I take complement of negation of n minus 1, if I take negation of n minus 1, what that will become? That will become this complement of this a, complement of this 0 will be 1, complement of this all these ones will be zeros, right? So if I take negation of this n minus 1, that will become 0 0 0 0 1 1 0 0 0. So in n and negation of n minus 1, you can see that before the rightmost set bit, all bits are exactly opposite, and after the rightmost set bit, all bits are exactly same, and that are 0 only. That they will be always be 0, because this is the rightmost set bit and all the bits after the rightmost set bit will be definitely 0. That's why we have traversed here, na. If we have any set bit before this one, before this one, that then we would have stopped before it, right? So before this one, all the after this one, all the bits are 0 and 0 in the negation of n minus 1 also. And before this one, whatever bit I am having here, they will become complemented here in negation of n minus 1. So in general, I can say that any number n which is of form like this, a1 0 0 0, its negation of n minus 1 will be a complement 1 0 0 0. And what if I take and of n and n minus 1, what will happen? This a and a complement, they will get nullified. So I will be left with 0 only here, 0 0 0 0. This 1 and 1 will become 1 and 0 and 0 will become 0, right? So all the position except the position of this rightmost set bit will become 0. This is the position of rightmost set bit, which is our kth set bit. At that bit I got 1, and rest of the index, at all the rest of the index, I got the value equal to 0. So to find the rightmost set bit, just do this. To find rightmost set bit of any number, just do this. Take that number, subtract 1 from that number, take negation of that n minus 1, and do AND of those two numbers. This will give me the rightmost set bit of any number n. Now this will act as a mask. To check whether any number have kth bit set or not. We know that this, let's say this is at index k, and kth bit is set. So if I take AND of any number, let's say I take AND of this number x, and then let's say this value I'm calling it as mask. So if I take AND with mask, and in this x, if the kth bit is set, I will get result as non-zero. I'll get non-zero result. But if the kth bit is not set in x, then x and mask will result me 0 only, because AND with 0 will become 0, and we have one at this kth position only, right? So I can say that this is my mask. Mask is what? N and negation n minus 1. So to check if this number x have the kth bit as set or not, just take AND of x with mask. If I get a non-zero value, then it means kth bit is set. If I get a 0 value, then this means kth bit is not set. Okay. Now let's write the final pseudocode. Let's say this is my ARR, which have all those numbers, from which I have to find those two unique numbers, right? So first of all, I'll run a for loop, and let's say I'll declare a Zord value, initialize it with 0, and I'll start my iteration from I0 till n minus 1, and I keep on zoring all the numbers. So Zord equals to Zor ARR I. So after the end of all these iteration, In Zord, I will have the Zor value of those two unique numbers, right? Now I have to take the Zor of group 1 and initialize it with 0, and I have to take the Zor of group 2, initialize it with 0. Now iterate from I is equal to 0 again in the array. If first I'll check for group 1, check if ARRI belongs to group 1. How will I check? I'll just do the AND of array I with the mask. How will I prepare mask? Mask will be nothing but rightmost set bit of the Zord value, right? So mask will be Zord and negation of Zord -1. So I got the mask here. So take AND of ARRI with mask. If that is a non-zero value, then if that is not equal to 0, and that means our rightmost set bit of the Zord value, set bit of mask is also set in ARRI. Okay, then take the Zor of this value in group 1. Else it will belong to group 2 only. So in that case, take the Zor of this ARRI with group 2. At the end of these iterations, in group 1, I will have the first unique number, and in G2 I have the second unique number. And just return these two numbers, G1 and G2. And of course we have to return them in sorted order. So if G1 is less than G2, then return G1 G2, else just return G2 comma G1 if G1 is not less than G2, right? So I hope you got it. If you still have any confusion, you can ask me in comments, and if you want the PDF of these slides, you can get them get them through the link in the description.